Hi, hello, welcome to this concluding lecture on CS700 Computer Science of Continuous Data Algorithmic Foundations of Numerics. Today we will recap the entire course, the entire content of this many sessions. Um, Next week there will also be some lecture, but these are not subject and relevant to the final exam and to your grades anymore. So the official part of the course ends today. And let me show you the slides. Here we are. Right. So this course would consist of 7 chapters. Chapter 0 about introduction and motivation. Chapter 1 with a recap of discrete computability theory. Chapter 2 about computability theory over the real numbers. Chapter 3 about computability on topological spaces. Chapter 4 with a recap on discrete complexity theory. Chapter 5 with complexity theory over the reals. Chapter 6 with complexity on metric spaces. And chapter 7 about imperative real programming. So that's 8 chapters since 0 is also included. Let's have a look at the content of each of these chapters now. So in chapter 0, introduction, we would recall the virtues of computer science, which happen to coincide or be very similar to the virtues of mathematics. We discussed the practice and benefits of data abstraction in computer science and mathematics and compared their similarities, such as information hiding and specification, or in mathematical terms, axiomatizing data types. Then we would consider the discrepancies between hardware data types and mathematical structures and how to and which of these discrepancies have been removed. For example, mathematical integers versus bytes and mathematical integers coinciding with big num, and mathematical real numbers different from floating point numbers. And the content of this lecture, or part of this lecture, is about making mathematical real numbers agree with computer science data types. We discussed the difference between programming and software engineering, which in the early times of computers was basically the same, but with nowadays huge projects, programming doesn't get very far. We discussed classical numerics, which is based on the IEEE 7454 standardization of floating point numbers from 1985, that is 35 years ago, and the consequences of that engineering approach to processing continuous data by a discretization, which hampers reliability in numerics, as we've seen with various examples. And we've started talking or capturing folklore and myths in numerics, such as avoid comparing by equality and computing integrals is easier than maximization, and computing roots of real numbers is possible. And that motivated us to look at these folklore and myths more precisely, more rigorously in terms of computer science of continuous data. Before that, we would recall The classical, that is the discrete theory of computability over discrete data, starting with the halting problem, formalizing computability and uncomputability, and semi-decidability using notions of reduction. The model of computation which we use throughout this lecture is the WILD program, which is more closer to practice than the original Turing machine model, but I have taken care to design WILD programs such that they are equivalent to Turing machines, just more convenient. We discussed the SMN property and currying of computable functions of several variables, and we discussed higher order computation involving oracles. That we discussed the Schoenfeld limit lemma and the arithmetic hierarchy of higher and higher uncomputable, undecidable problems. Then we would adapt these notions, concepts from the discrete setting to the real setting. Our real setting is usually the guide and transition to the more general setting of more general and abstract spaces. So computability theory of the reals. We discussed different notions of computability for real numbers and established them as equivalent. We discussed examples of computable real numbers and counterexamples of uncomputable real numbers and oracle computable reals, real counterpart to the arithmetic hierarchy. And we would proceed kind of to more advanced data types over the real numbers, specifically computable real sequences. We discussed the question of whether equality is decidable or not in this rigorous setting and gave a strong and formal statement and proved a strong and formal statement establishing that equality of real numbers is indeed undecidable in a rigorous sense. And we also proved that although the set of computable real numbers is countable, it cannot be captured by a computable sequence, which is also a countable number, also encompasses a countable number of real numbers. Every computable sequence must necessarily miss at least one computable real. And then we continued climbing up the type hierarchy from single real numbers via sequences of real numbers countable to kind of uncountable, namely computing real functions. Again, discussing three possible definitions and their properties, specifically closure properties. We want computable real functions to be closed under composition because that's an essential part of software engineering, modular software engineering, which is true in the discrete case. So we want that also to carry over to the real setting. We want that the restriction of any computable real functions again computable, and we want computable real functions to map computable sequences to computable sequences. And we saw that the definition we thus arrived at requires any computable function to be necessarily continuous. And for uniformly continuous, for continuous function on the compact domains, we established a computable version of the classical Weierstrass theorem, saying that a function is continuous if it can be uniformly approximated by polynomials, now here by computable polynomials. And that proof led us to discuss quantitative strengthening of qualitative continuity captured in terms of a modulus of continuity. And we would proceed to discuss examples of computable real functions and counterexamples of uncomputable real functions. That would involve uncomputable cases of the derivative, the Myhill's example, uncomputability of the wave equation, uncomputability of root finding, and discussing how to turn all these counterexamples into examples by imposing additional hypotheses or additional restrictions, such as, for the derivative, supposing that the function is actually twice continuously differentiable for the wave equation by proceeding to an appropriate Sobolev space, or for root finding by requiring the function to have a unique and simpler root. And we would discuss multifunctions as a way of dealing with naively uncomputable, namely discontinuous functions, specifically the sine and Heaviside function relaxed into multifunctions turned out to be computable. And we would discuss enrichment as another way of turning or avoiding the obstacle of discontinuity. So for multifunctions, there we saw that there are two notions of restriction, one that makes the domain smaller and one that makes the range larger. And a prototype example application of multifunction is the fundamental theorem of algebra, where the set of roots of a given polynomial is not unique, only unique up to permutation. So it's kind of root finding in this sense is a multifunction. We would discuss the multi-valued generalization of the sine and Heaviside function, which is sometimes called the fuzzy sign, and show that these are actually computable. And we will discuss the Archimedean property of real numbers, which again only becomes computable after relaxing from function to multifunction. Actually, yeah. And we would discuss computability in linear algebra, where we would need enrichment, namely additional discrete information as part of the input matrix, such as its rank, which is discrete and uncomputable, but when providing this addition as input, renders many operations in linear algebra computable. And similarly for analytic functions, we also saw that in general, given a power series, the function associated with that series is not computable, but when providing additional discrete information about the rate of growth, or rather decay of the coefficients, then it becomes computable. And finally, we will discuss computing real operators, another step up the type hierarchy, which requires discussing how to encode the functions as input, right? So computing real functions would involve real numbers as input. Computing real operators and functions would require real functions, continuous functions as input. And one way of encoding this is using the Weierstrass theorem, encoding this as sequences of rational polynomials. We would discuss uniform computability of operators where the function is actually given as input, and non-uniform computability where the function is arbitrary computable but fixed. And an important difference is that for uniform computability, when the function is actually given, it need not be computable. It's possible to input uncomputable real numbers to computable real functions, and it's possible to input uncomputable but continuous real functions to computable operators. And another higher type is operating on compact subsets, which again required us to discuss how to encode such compact subsets. And we discussed which Boolean operations on compact subsets are computable. It turned out that union is, but intersection is not. Okay, that was about computability over the reals, and that served for us as guide to discuss now computability over more general and abstract topological spaces in chapter 3. So in chapter 3, we would discuss computing over basic spaces being the spaces that our programs, while programs or Turing machine can naturally operate on without having to discuss coding issues. Basic spaces thus incorporating Cantor space and Baire space, and we formalize what it means to compute on them. We discussed notions of computational cost, computational complexity, and how the two are related. Specifically, we showed that if a function on from to pair space is computable in time t, then t is a modulus of continuity of that function, necessarily giving a quantitative strengthening of the qualitative main theorem that any computable function must be continuous. But now here, for now restricted to the case of these basic spaces, Cantor and Baire space. And we discussed the importance of compactness, both turning continuity into uniform continuity and turning computability into resource-bounded computability, worst case computability. There is a worst case over any total computation over compact subset of Cantor and Baire space. Then from there, we would proceed to discuss computing over more general and abstract topological spaces by encoding them over basic spaces. And these encodings were formalized as so-called representations in the type 2 theory of effectivity of Weyrauch. So we define what the representation is, and we would consider several representations of the real numbers that would recover our previous ad hoc notions of computability over the reals. And we discussed what the realizer is, realizer of a function or multifunction between two spaces, topological spaces, when equipped with such representations, such encodings. And we would start comparing such encodings, such representations by means of computable or continuous reduction. And we discussed standard representations and admissible representations, and the main theorem of Kreitzer and Weyrauch from 1985, showing that any topological T0 space with a second countable basis actually has an admissible and even a standard representation, and that these representations are the ones that translate continuity of functions to continuous realizers and vice versa. And then we would discuss induced representations for sequence spaces, induced representations for spaces of continuous function, and induced representation for space of hyperspace of compact subsets. Then we'll proceed from qualitative computability to quantitative complexity. Again, first doing a recap of the classical discrete case, and then proceeding to the real case, and then finally generalizing that to metric spaces. So in the discrete complexity recap, we would discuss computation with cost and the importance of asymptotic growth of computational cost. We would discuss complexity of arithmetic in our while plus program model. We would recall selected complexity classes such as P and NP, but also P space, and later sharp P as a countable complexity class. But for now, we were still focusing on decision problems. We would discuss several example decision problems, most of them about graphs, and would classify them in these classes, such as, for example, the Hamilton cycle problem, the Eulerian cycle problem, the clique problem, the independent set problem, the vertex cover problem, and the edge cover problem. And we would compare the intrinsic computational complexity of these problems, first in the intuitive sense, that there's an equivalence. If there's a polynomial time algorithm for one, then there's also a polynomial time algorithm for the other, and then formalizing that in terms of reductions. And that led us to this complexity class picture, this kind of Venn diagram with the hardest problems being the complete problems. Then we would discuss more advanced topics on discrete complexity theory, such as the aforementioned counting complexity class Sharpie, which is a class not of decision, but of counting problems. We would discuss unary versions of the previous complexity classes, where the inputs are restricted to be integer powers of 2, or put differently in terms of binary representation just using unary encoding. That's why it's called unary complexity classes. We would discuss parameterized complexity, which considers two complexity parameters. One, our usual binary input length, and then there's a second complexity parameter, which is usually chosen in an ad hoc wave. And we would discuss average case complexity to take into account that some problems may be hard on few instances, which then govern or determine their first case complexity, but are not really relevant maybe in practice because they may occur very rarely. And for average case complexity, we would consider some input distribution, probability distribution on the set of inputs, and then recall the carefully designed notion of average case polynomial complexity of Leonid Levin, which is not the naive notion that one would come up intuitively, because the latter is not closed under polynomial time reduction. And then we would recall various other kinds of reductions, variations of the polynomial time many-one reductions, also called Karp reduction, such as log space reduction, such as Turing reduction, and even reductions among function problems. And that was the conclusion of the chapter 4 recap of discrete and advanced discrete complexity theory. And then we would adapt and generalize that to complexity theory over the reals with polynomial time computable versions of real numbers, strengthening our computability of real numbers. We would discuss polynomial time computability of real functions, again, where the computably equivalent notions turn out to be complexity theoretically different and not equivalent, not polynomial time equivalent. We would strengthen our previous main theorem, the Kreuzfeuerbach main theorem, that computability implies qualitative continuity, to show that quantitative computability implies quantitative continuity and observation that maybe dates back to Carey-Coe. Then we would consider the computational complexity of operators, but only in the non-uniform setting, where we would fix an arbitrary polynomial time computable function and ask whether the result of the operator, such as the antiderivative, the indefinite Riemann integral over this function, or the maximum of that function as a functional, or the derivative of that function is again polynomial time computable. And then we would discuss two notions of polynomial time computability for real sequences. The first notion, where the sequence index is given in binary, and the other notion where the sequence index is given in unary. And then we would consider polynomial time computability for the restricted case of analytic functions. See that there two notions of polynomial time computability indeed agree. One, the notion of polynomial time computability as a function, and the other, polynomial time computability of the Taylor series coefficients as a polynomial time computable real sequence. And then we would discuss operations that preserve polynomial time analytic functions, such as indefinite Riemann integration, antiderivative, or derivative. And then we would similarly ask the same question for the computable polynomial time computable functions without being analytic. And we saw that in general, indefinite maximization in a sense lies in the complexity class sharp P, and here the statement is deliberately put in quotes because NP, as you know, is a class of discrete decision problems, and here we talk about continuous functions problems, but the rigorous statement was expanded on in that part of the lecture. Similarly, we showed that indefinite Riemann integration, that is antiderivative in a certain sense, belongs to this complexity class sharp P, and definite Riemann integration, even in the unary version of that complexity class sharp P unary. And solving ordinary differential equations, which turned out to belong to the complexity class P space, as attained both by Euler's method and by higher order Runge-Kutta method, all incur computational bit costs corresponding to polynomial space. So from this rigorous perspective, the advantage of Runge-Kutta method over Euler method is kind of negligible. It's only polynomial acceleration, but the overall cost is exponential in for any of these algorithms. That led us to the question whether these upper complexity bounds are optimal, and we saw that indeed they are. Parametric maximization is in a certain sense NP hard. We constructed it in this artificial but still relevant polynomial time computable function whose parametric maximum is not polynomial time computable unless P equals sharp P. We similarly showed that indefinite Riemann integration is also in a sense hard for these complexity classes sharp P and sharp P unary. And then we would proceed to more advanced numerical problems, specifically to partial differential equation. And we would discuss the Poisson and the heat equation and see that Poisson's equation is, in a sense, belongs to this complexity class sharp P1 and is in a sense complete for that, and similarly for the heat equation. And then we would discuss more numerical characterizations of discrete complexity classes. Okay, that was the wrap up of our chapter 5 on complexity theory over the reals. And that served for us as guidance to complexity considerations on abstract metric spaces. We would define the complexity of single elements on such an abstract metric space, the complexity of functions between metric spaces, and raise the question whether our connection between computational cost and quantitative continuity from the real case carries over to metric spaces. And to this end, we would quantitatively refine qualitative admissibility, the notion of Kreitz and Weyrauch, to polynomial admissibility, and develop a polynomial version of the qualitative Main theorem of Kreitz and Weyrauch, which connects quantitative continuity of a function to quantitative continuity of a realizer of that function, subject to the representations under consideration to be polynomially admissible. And the notion of polynomially admissible would involve a quantitative version of qualitative compactness, which is the entropy as introduced by Kolmogorov. And we proved that every compact metric space has a standard representation, which is a particular case of polynomially admissible representation, a quantitative version of the Kreitz-Weyrauch theorem, that every second countable T0 space has a qualitatively standard representation. And for spaces of exponential entropy, that is such as function spaces, we would extend our list of basic spaces from Cantor and Baire space to second order basic spaces. And that section would then devise a kind of a dictionary translating between qualitative and quantitative properties, translating between computability and complexity, topology to metric, uniform continuity to quantitative modulus of continuity, Qualitative compactness corresponds to quantitative entropy. Continuous image of a compact set is again compact, and Florian Steinberg's lemma relates the modulus of continuity to entropy. And equilogical spaces as a general class of basic spaces for computability investigations has a counterpart of compact ultrametric spaces as a category of basic spaces for complexity considerations and quantitative encodings. And finally, we proceeded and closed with proceeding from all these theoretical considerations to actual practical programming. Namely, how can we develop a rigorous foundation of the intuition that most numerical programming actually implicitly is based on, since floating point numbers are not a suitable rigorous foundation. They differ, and thus the programs over floating point numbers differ from the consideration of actually operating on real numbers. And indeed, the notion of computability of real function that we employed throughout this lecture is great for investigating purposes, for theoretical and structural and conceptual purposes, but very inconvenient for actual programming. And to this end, we would extend our while programs, which were so far while programs over integers, to while programs over the reals, but these were insufficient because we cannot have the integers encoded in the reals for continuity reasons. There's no integer rounding, computable integer rounding. Instead, we would consider while programs over three sorted structure, integers, real numbers, and this special three-valued logic type, data type, Kleinian logic. And we would consider non-extensional version of an integer rounding, which we know is computable, for which we would actually devise imperative program. So not the stream-based approach, but real imperative program. Actually two such programs, a naive one with, in a sense, has exponential number of loop iterations, and a fast one which has only a polynomial number of iterations of the loop. We would discuss a rigorous algorithm for the exponential function, which is actually the algorithm that everybody uses in numerics, but now with a rigorous foundation where we can indeed operate on the real argument exactly and compute the first n terms of the Taylor expansion to achieve and arrive at the approximation of the exponential function. And then we could consider an algorithm for a functional, namely for a simpler root finding, and namely a formalization of the trisection method, which involves multi-valued computation. And finally, matrix determinant computation using a computable version of Gaussian elimination using multi-valued pivoting, you would call multi-valued computation. And finally, we would show that this new model of computing over continuous data over real numbers is actually Turing complete. It can express precisely those real functions that are computable in the stream sense, but now more conveniently in the way that a numerical intuition actually works by processing real numbers exactly and returning approximations up to any given absolute error 2 to the minus n. So that was this course. I've enjoyed a lot designing and teaching you this. I hope this is an accessible approach to real computability and complexity theory. And want to thank you very much for joining this course, and all the best wishes. Goodbye.